In this video, I'll be talking about Experiment 6, which talks about aqueous reactions. In Experiment 6, we're going to be thinking about single displacement and double displacement reactions, but since we focused quite a bit more on double displacement reactions in Experiment 4, we're going to think a little bit more about single displacement reactions in this handout. One thing that's sort of a new idea in Experiment 6 is using the activity series. So the activity series tells us the ability of a metal to be oxidized. So when we're using the activity series, which can be found in your lab manual on the second page of Experiment 6, we have to think about how we use the activity series. So when we're using the activity series, metals, or the thing that is a solid in our reaction, have to be above our ion solution, so the thing that's aqueous in your reaction, in order for a reaction to occur. So this tells us that the metal is more reactive than the ion. So if a reaction occurs, that means whatever is the solid in your reaction is more reactive than whatever was the ion or the aqueous species in your reaction. If no reaction occurs, that means that the metal, or the thing that's solid, is less reactive than your ion or whatever was aqueous in your reaction. When we're writing balanced redox reactions, there are a few rules that we need to keep in mind. One thing that we don't think about as much when we're balancing double displacement reactions is the charges. So whatever charge you have on the left side of a reaction, on the reactant side, has to be the same as the charges on the product side, keeping in mind that the charges will not necessarily be, and in fact can't be, on the same atom. Once you've balanced your charges, you also have to balance your atom count. And again, the charges should not stay on the same element because otherwise it's not a redox reaction. So redox means that we have the transfer of electrons, and so the charges will be changing. When we're thinking about water in a redox reaction, it helps to think about it as HOH. So in the single displacement, some species is going to pick up the hydroxide ion, and generally one of the products will be H2. And if you see two ions or two metals, they will not react because for redox to happen, you have to have both reduction and oxidation. So if you have two ions, meaning that both things are aqueous, or two metals, meaning both species are solids, then we will say that there is no reaction. So let's practice. Let's say we're reacting potassium with copper 2 chloride. So the way we write that is potassium plus copper 2 chloride. So we need 2 chlorides to make that reaction occur. Because potassium is above copper on the activity series, we'll have a single displacement occur. So the K will pick up Cl, and according to your solubility chart, that's aqueous. And the other product is copper in the solid state. Then we balance this equation, and this reaction should occur. It's also helpful to think about the net ionic equation that takes place here, so we can think more about what's happening to the charges. So the complete ionic equation is where we break everything up that's aqueous and soluble, so a strong electrolyte, and we assign charges to everything. So we'll have copper 2+ ions, 2 chloride ions, and on the product side, our potassium chloride is going to break up into 2 potassium ions and 2 chloride ions. And since copper's in the solid state, it will remain as is. Now when we're thinking about the net ionic equation, we need to cross out things that are the same on both sides. And then for our net ionic equation, we'll have two potassium solid, so no charge on the potassium at the beginning of the reaction, plus copper 2+ ions. And now notice what's going to happen is the potassium is going to end up with a charge, and copper will end up with no charge. Let's look at the next one. So we have magnesium plus water. Again, think about water reacting as HOH. So we've got magnesium reacting with water, which is a liquid. Magnesium's going to pick up the OH, and because magnesium's a 2+ ion, it makes magnesium hydroxide, which according to our solubility chart is a solid, and the other product is H2 gas. And we need to make sure that this reaction is balanced, so we put a 2 in front of the water. Next, we have zinc plus lead nitrate. So we'll start by writing out the complete equation. So zinc plus lead 2 nitrate means we need 2 nitrates to make that a neutral compound. All nitrate salts are soluble, so we'll write aqueous. And so now the zinc picks up the nitrate. According to the activity series, zinc is also a 2+ ion, and the other product is lead, so that would precipitate out. This reaction is balanced, so we can go ahead and write the complete ionic equation. Zinc reacts with lead 2 ions. We also have 2 nitrate ions present. And on the product side, we have zinc 2+ ions, so notice the charge, and 2 nitrate ions, and lead in the solid state. So again, we're going to cancel the things that are in common on both sides. And our net ionic equation is zinc plus lead 2+ ions react to make zinc 2+ ions and lead solid. So notice what's happening is that zinc is giving its electrons to lead, and so zinc loses 2 electrons to make the 2+ ion. Lead gains 2 electrons to become neutral. And so what you would visualize here is the zinc dissolving into solution, and the lead would be precipitating out. So the zinc dissolving means the solution is going to be clear and colorless. The last reaction we have is copper plus iron sulfate. So we've got copper plus iron 2 sulfate. With this reaction, we're going to write Nr because Fe is higher on the activity series, so no reaction occurs. And you'll be able to see that when you put those 2 substances together in your test tube in this experiment. So the things we'll be doing in this experiment will be reacting metals with HCl and water and metal ion solutions to determine the activity series. And the most important part that we're going to be doing is writing balanced equations for these processes so that we can make our own activity series. We're going to predict whether precipitation will occur, and this is using our solubility rules. And we'll use the solubility rules to identify an unknown, so thinking about whether something precipitates or not. And that's experiment 6.